Good morning, everyone. Thank you for joining this section. My name is Mustafa Istanbullu, and today I will be presenting our recent work on a planar surface electrode system developed for electrical impedance tomography. This work is the result of an effort to improve the practicality, resolution, and cost effectiveness of electrical impedance tomography systems, making them more suitable for both clinical diagnostic and experimental research. Let me start by briefly outlining today's talk. We will begin with the motivation behind this study and discuss what makes electrical impedance imaging a compelling tool. Then I will give a bit of background on electrical impedance tomography and explain the limitations that we aim to overcome. From there, I will describe our design and the rationale behind its structure. We will talk about frequency selection, walk through the hardware architecture, and then move into simulation and experimental validation. Along the way, we will discuss modeling strategies, image reconstruction methods, and of course, share the results, both simulated and real ones. Finally, I will wrap up with a summary and touch on future directions for this work. Let's begin with some context. Accurate and non-invasive imaging techniques play crucial roles in diagnosing and monitoring various medical conditions, offering safer alternatives to conventional methods. Bioimpedance measurement provides a practical approach to assess internal structures by injecting an alternating current into the sample under test and measuring the resultant voltage distribution. Electrical impedance-based imaging offers a unique set of advantages. It's non-invasive, radiation-free, low-cost, and highly portable, which makes them appealing for use in dynamic bedside or point-of-care scenarios. However, conventional electrical impedance tomography systems are not without challenges, of course. Most use circular or bracelet-style electrode arrays, which are often difficult to place around the body, especially in constrained or irregular regions. In some cases, the area to be measured cannot be completely surrounded by electrodes, or the process of placing the electrodes regularly and appropriately around the measurement area may be time-consuming and difficult, maybe. These limitations underscore the need for a planar electrode arrangement, which offers improved adaptability, especially in challenging anatomical or experimental setups. They also involve complicated wiring and suffer from lower spatial resolution compared to the imaging modalities like computed tomography or magnetic resonance imaging. Our aim was to develop a more accessible, surface-based system that provides rich spatial information without needing a fully wrap around the body. So, how did we approach this? We took inspiration from the scanning principle used in computed tomography, where multiple angular projections are collected to build a complete internal image. In computed tomography, the X-ray source rotates around the body, but in our design, we mimic this concept using a rotating electrode-based stimulation and measurement strategy, while keeping the entire setup planar. I mean, all electrodes are mounted on a flat surface. This allows for simplified setup, easier fabrication, and potentially broader use cases. Now let's look at our design shown here in figure 1. We arranged 32 electrodes in 4 concentric circular rings, each with 8 electrodes. These are divided into 8 directional lines labeled A through H. Each line runs from the center to the periphery. In each measurement cycle, an alternating current is injected between the first and the last electrode offline, and voltages are measured from the remaining electrodes with respect to the current sink. This configuration rotates through 8 directions spaced at 45 degrees intervals, resulting in a total of 240 voltage measurements. It provides multi-angle impedance data similar in speed to what computed tomography does with X-rays, except we use current flow, of course. Now, why 1 kilohertz we select? That brings us to figure 2. Biological tissues exhibit frequency-dependent electrical properties, generally described in 3 dispersion regions. First one is the alpha dispersion up to 10 kilohertz, is dominated by ion movement and membrane polarization. And the others, beta and gamma dispersions, involve intracellular and molecular effects occurring at higher frequencies. We choose a 1 kilohertz and 10 milliamps excitation current, which places us in the alpha region, making it well suited for detecting differences near the tissue surface, such as inflammation, cysts, or tumors. It also balances depth sensitivity and resolution without excessive signal attenuation. Here in figure 3, you see the block diagram of our full system. Let me walk you through each model. First one is the Phantom, this one. This is a 3D printed saline filled tank to mimic the conductivity of biological tissue. Its embedded anomalies represented abnormal regions. Next, the signal generation and injection module is an AD9833 waveform generator produces a 1 kilohertz sine wave. Then the signal is amplified and sent to the Howland current pump, which acts as a voltage-controlled current source. And last, a class AB output stage ensures efficient current delivery. Then we have the electrode switching module here. An analog multiplexers dynamically select which electrodes inject currents and which electrodes measure the remaining voltages. And finally, we have microcontroller unit. Here we used an Arduino Mega to control the switching timing and also communication. And finally, we digitized signals. The digitized signals are sent to a MATLAB interface for image reconstruction, of course. And each model is designed to be low-cost, modular, and easy to integrate. This figure shows how this comes together physically. On the top left, we see the current or voltage module. In the top right, the switching circuitry and phantom tank. You can see from top right figure, and the bottom figure, the assembled system, compact and easy to deploy. The phantom tank is 15 centimeters in diameter and 3 centimeters deep, and it's filled with a saline solution at 4 grams per liter. These small copper electrodes, which are 0.5 centimeters in diameter, are embedded at the base, and a rubber marble serves as an artificial inhomogeneity. You will see that rubber marble in the I think the following figures. There's absent here. Before experimentation, we simulated the setup using ADORS, which is a MATLAB-based open source electrical impedance tomography framework. This environment provides a comprehensive set of tools for forward and inverse modeling, facilitating accurate simulation and evaluation of electrical impedance tomography systems. We modeled a block domain with a surface electrodes layout, and spherical inhomogeneities were placed within the volume, this one. In figure 5, you can see the test geometry and the electrode arrangement on the top surface. This simulation helped us fine-tune our current injection and voltage measurement schemes. Figure 6 and 7 present our current injection and voltage measurement patterns. This stimulation pattern is designed to apply controlled current injections through the electrodes. Each stimulation pattern specifies the combination of a positive and negative current sources on designated electrodes, ensuring that the applied currents follow the defined injection profile. Simultaneously, voltage measurement patterns are defined to determine the potential differences across the selected electrode pairs. This dual approach enables comprehensive data collection for the reconstruction process. The current stimulation matrix is presented in figure 6, this one. In this matrix, stimulation A, stimulation B as stim A, stim B, and up to stim H represents the individual stimulation configuration, while the numbers from 1 to 32 correspond to the electrodes labels. For example, in the stimulation A configuration, a 10 milliamp AC current is applied between the first and eighth electrodes, as indicated in the values of 0.01 and minus 0.01 in respective columns. The zeros in the remaining entries of the stimulation A row signify that no current is injected through the corresponding electrodes. Similarly, for the stimulation B configuration, current is applied between the 9th and 16th electrodes. This pattern continues for all measurement configurations, each corresponding to a unique pair of electrodes with a 10 milliamps AC current injection. The measurement pattern for stimulation A is also represented by a 32 by 32 matrix in figure 7. In this figure, the numbers in the top row indicates electrode numbers from 1 to 32, whereas the numbers in the first column indicates individual voltage measurements. Again, starting from 1 to 32, of course. The values with the matrix determine the electrode rows during measurement. For example, a value of 1 represents the active electrode for voltage measurement, whereas a value of -1 indicates the reference electrode used for voltage measurement. A value of 0 represents inactive electrodes during the measurement. This pattern results in a total of 240 voltage values across 8 directions, providing rich spatial information for image reconstruction. Now let's talk briefly about how we turn this data into images. Once all the measurements have been accurate and recorded as described, the process proceeds to the image reconstruction steps. The forward problem, which calculates the voltage distribution on the basis of the non-conductivity distribution and applied current pattern, is solved with the finite element method. The finite element method formulation employs the governing differential equation as given in the first equation, where a sigma is the conductivity distribution and phi is the electrical potential. This equation is solved under appropriate boundary conditions to ensure accurate modeling of the system's electrical behavior. At the boundaries where electrodes are present, Neumann boundary conditions are applied such that the normal current density is specified as given in the second equation. Here, n is the unit normal vector pointing outward from the boundary surface, and del omega is the geometry boundary, and J is the current density at the electrode boundary. The resulting voltage distribution is calculated with the system matrix formulation as given in equation 3, where A is the system matrix, P is the nodal potential vector, and again J represents the injection currents. The system matrix A is constructed on the basis of the finite element method, discretization of the governing equation, and is defined as in equation 4. Here, omega is the domain, and Ni and Nj terms are the shape functions used in the finite element method to approximate the potential distribution within each element. The inverse problem aims to reconstruct the internal conductivity distribution by analyzing the measured voltage data. This is achieved by minimizing the difference between the predicted and observed voltages. The reconstruction process employs a Gauss-Newton method combined with regularization techniques to enhance the image stability. The inverse problem is formulated as an optimization problem to minimize the objective function as given in equation 5, where V measurement is the vector of the measured electrode voltages, and V calculated is the predicted voltage vector that's calculated from the forward model, and R of sigma is the regularization term. The parameter lambda controls the balance between data fidelity and regularization. Lastly, the Jacobian matrix J is calculated to linearize the nonlinear relationship between voltage and conductivity, enabling iterative updates for conductivity estimation. Its formulation is given in equation 6. In this study, a difference imaging approach was employed to solve the inverse problem. Initially, baseline voltage measurements were obtained from a homogeneous medium, followed by a second set of measurements after introducing an inhomogeneity. The difference between these two data sets was used as the input for image reconstruction. The forward problem was solved using finite element method, and the Gauss-Newton algorithm with total variation regularization was applied to iteratively estimate the conductivity distribution. This framework enabled the effective reconstruction of internal conductivity variations based on the differential voltage data. A flow chart of this of the entire algorithmic process is illustrated in this figure, in figure 8. Now these are simulation results. Figure 9 shows the simulation outcome. The top two figures are the defined medium with inhomogeneities. These black ones are inhomogeneities, you can see from here. The middle ones are reconstructed impedance maps, and the bottom ones are the top-down view of showing the alignment with the electrode layout. The system, as you can see, the system accurately localized two anomalies, even with close spacing. This confirmed the effectiveness of our electrode configuration and measurement protocol. Now, in real-world tests, we repeated all the process using the phantom tank. You can see from here. In figure 10, the top row figures show the positions of the rubber marble within the saline film tank, while the middle figures show their impedance distributions. These figures demonstrate the ability of the system to find the locations of inhomogeneity with impedance values higher or lower than those of the surrounding saline solution, while also providing information about their locations. Although the resulting reconstructed images provided a preliminary visualization of impedance variations and the approximate locations of the inhomogeneity within the phantom, further image processing was essential for clearer delineation of the boundaries and more accurate localization of the detected anomaly relative to the electrode configuration. To achieve this improved visualization, a sequence of image processing techniques was then applied. Initially, the color image produced by ADORS was converted to the grayscale to simplify the subsequent processing steps. The grayscale image was then normalized, standardizing the pixel intensity values for consistent thresholding performance. Medium filtering was applied to the normalized image to reduce inherent noise, thus enhancing the clarity of the meaningful impedance variations. A thresholding procedure was subsequently employed to segment the impedance anomaly from the background, creating a binary image representation that clearly distinguished the inhomogeneous region. Finally, labeled regions were identified and boundaries of the impedance anomalies were visually overlaid onto the original normalized image, as well as the electrode arrangements, as shown in the bottom row figures. This overlay visually verified and preciously localized impedance anomalies relative to the electrode positions. To summarize, we developed a multi-angle planar electrode system inspired by computed tomography geometry. We built a low-cost portable measurement platform, and it's validated its effectiveness by both simulation and experimentation, and introduced an image processing pipeline to enhance boundary localization. This design strikes a balance between simplicity, accuracy, and practical deployment. I think this was my last slide. Thank you for your listening. If you have any question, you can mail me. Thank you again.